In this module, we'll cover first order transient circuit. So let me explain what do I mean by first order and what do I mean by transient circuit. And the simplest way to do that is with a simple example of what we call an RC circuit. And it's called RC because it has a capacitor and a resistor, or maybe a capacitor and a resistor in here. So this particular circuit has a switch in it, and the switch actually results in a couple of sub-circuits. So the first one is when the switch is at A, what we have is we have a voltage source connected to this resistor R1 and then the capacitor in here. And we know, of course, if the capacitor is connected to a DC source, that if you wait for some time, that source will provide some sort of a charge into it, or it will charge the capacitor so that the capacitor will store some energy. So after a while, what we will see is it's pretty much this one here is R1, and this one here is just simply an open circuit. And in this particular open circuit, the voltage across it in here, which is at that point we can call it VC, is the same as VS. All right, and at some point what we have, and that point is we're going to consider it to be T0. What we do is we take the switch from point A to point B in here, and that will result in the following circuit, which is the capacitor just simply connected to a resistor in here. And of course, the capacitor initially it always will have some sort of a VC. Okay, and VC of course is a function of time in here, and it's a function of time in here, and initially it will also have a VS, and because it has a VS initially, so that means the R will have a VS across it. That means there will be a current flowing through it. So the current flows through it, but of course R consumes the energy and basically produce something useful with it, and after a while R will consume all the energy that is stored in the C, and that's it. The capacitor will lose the charge, will lose the energy, and that's it. So we won't have any current flowing through it. So that's pretty much what's happening in this circuit. So let me just plot with time what's happening with VC. So let's assume that I have some sort of a y-axis in here, and I have some sort of an x-axis in here. And the x-axis will have a T, and the y-axis will have the voltage across that C in here, which is basically from here to here. So that we know is a function of time. So what I'm saying in here is if we were in point A for a very long time, and I'll refer to what very long time to, or I'll explain what very long time soon, but at some point you will see that what you will have in here is some sort of a charge across that capacitor, and that charge is exactly, its value is Vs, which is the voltage source that we see in here. That's basically this particular case. And at time 0, what we have is, and let's assume that this is here is time 0, what we have is the switch basically goes from point A to point B, and of course that results in this particular case. And of course the voltage across it will actually slowly drop. And the reason why it slowly drops is, if you remember, what we have is I equals C times dV divided by dt. This is basically the current across the capacitor, and this tells me because of the dV, well, if dt goes to 0, that means the whole thing in here goes to infinity. That means the whole thing here goes to infinity. And if you remember, we said like this cannot happen. So that means, which in other words says the voltage across this capacitor, which the one we're drawing, cannot jump directly from 0 to some sort of a value. So it has to have some sort of a time delayed by the drop. So in here, okay, going back to the point that I'm trying to make is, well, after a T0, what we did is we switch, and then the capacitor starts basically releasing its energy to R, and that release will actually take some time, and it will actually go all the way down to 0 in here. And then if we stay at point B in terms of the switch, that will stay for as much time as we stay in B. And then let's assume that after what we did in here, what happens, like, okay, we were at B, and then I decided, you know what, I'm going to go back to A. So when you go back to A, you'll get this particular circuit, and of course initially VC will not have any charge in it because it emptied all the charge or all the energy in R. So what happens is there will be some sort of a current to charge C, and again we can't just directly jump to Vs because the capacitor opposes changes in voltage. So that particular change will actually happen also slowly in here with some sort of a time, and then eventually you'll get the same Vs as before. So you will get some sort of a switch in here. So there will be switching in here and switching in here. Those are the places where the switch happens, okay? All right, so if you take a look at you will know that the voltage across the capacitor is actually changing with time, and it has a few states in here. So in this particular state, let me just highlight it. This particular state in here, and this particular state, and these particular states are what we call a steady state. Steady state, that means there's no change with time. In terms of DC circuits, there will be no change of time. If it wasn't a DC circuit, you will see that the source will be just basically not necessarily a constant value, but it will be basically stabilized. It's the same thing. It's a steady state. That's what we said. And the other cases is here, which is basically these changes from here to here and from here to here, and that's what we call transient states. So as it turns out to be that these RC circuits or RL circuits, as we'll see as well, have steady states and transient states, and we're interested in studying these transient states, like how long does it take to go from this steady state to this steady state, and how long does it go back from this steady state to this steady state, and we'll see all of these in this particular module. Anyhow, so this is why we call these transient circuits, okay, because they have some sort of transient states. So why do we call them first order? Because as it turns out to be that these circuits in here, and no matter how complicated the circuit that is connected to capacitor, we can technically, if you think about it, this is basically the Thevenin equivalent to some sort of a circuit. So this part of the circuit, this one here, it can be as complicated as you want it to be. The one that is connected to capacitor, you can just compute the Thevenin equivalent. And similarly, on the other side, you can pretty much combine a bunch of resistors together to actually get some sort of an equivalent resistor. And if you were able to reduce the circuit to this particular shape, where you have like some sort of a voltage source or a Thevenin equivalent on this side and an R on this side, you will be able to describe the circuit with a simple differential equation that looks similar to this. So the solution for all the circuits, what we will see in this module, will have this particular shape. In this particular shape, the X represent either V or I, depending on what you're looking for. It's either voltage or current. In any way, what you will see, it will have some sort of a derivative or the partial derivative of V or I. Let's call it X for now. And it will also have the actual function that I'm looking for, which is V or I, which is X in this particular case. And of course, there will be 1 divided by tau. This is what we call in here is time constant. Okay, and I'll talk about it briefly in a few minutes. Okay, and in here it's actually just some sort of a constant. In DC circuit, it could be either 0 or some sort of a constant value. Okay, if it wasn't a DC circuit and we have something more complicated, instead of constant value, it will be some sort of a function of time, like a cosine or sine or something like that. But anyway, the reason why we call these circuits as first order circuits is because of the following: because we can describe all of them, or the behavior of the voltage or current, using this particular equation. And this particular equation contains the function and its first order or first partial derivative, not the second part derivative, just the first. And that's why we call it first order, because all these circuits, if they contain an RC or an RL, as we will see, pretty much we'll be able to describe it with a first order differential equation circuit. And it's this first order, let me just emphasize, because it contains only one capacitor. That's why. It's first order because it contains one storage element, not two. Or it could be L for RL circuits. And of course, again, if you have multiple capacitors, you should be, if you can combine them into one, you will be able to describe them, combine them meaning like series parallel combination of capacitors or inductors. If you can combine them into one, and you can actually come up with this particular circuit, you should be able to describe it with this first order differential equation. If you cannot, that means the circuit is a little bit more complicated and it's outside the scope of this particular module, but you will be able to solve it with much more efficient ways than describing them with partial or differential equations. So you'll be able to take them to a different domain, like a Laplace or a phasor if you're dealing with sinusoidal, but that's outside the scope of this particular module. We'll cover it in a different module. So these RC and RL circuits are considered first order circuits because we can describe them with such equations, which are first order differential equations. And if you remember differential equations, the solution for first order differential equations will have some sort of a two parts, a particular solution and a complementary solution. Anyhow, at the end of the solution, what we will end up with is an equation that looks like this in here. And in this particular equation, we'll have x of t. And remember, x represents voltage or current, depending on what we're looking at, whether it's an inductor or capacitor, and some sort of a constant here and another constant and some sort of a decaying part, or like an exponential. And this exponential is with an e. Okay, so let me just talk a little bit about it. And in this particular solution in here, C1 and C2, I'm considering them constants because we're dealing with DC sources. If they were not DC sources, we'll have different functions of time in here. But let's focus on DC sources because the solution is pretty much, will have the same shape. It's just, this will be a function of time. This might be another function of time. But for now, we deal with them as constants just because mathematical simplicity. So we will have some sort of a constant in here and some sort of a constant in here. So let me just highlight them here for you. So this one here, I'll highlight it in blue because we highlighted this in blue a few seconds ago in here. Okay, so let's take a look. What did I highlight in blue? I highlighted in blue these particular two parts in here, which are the transient. Let me just see, why are they transients? Well, they're transient because we have the e in here to the negative t. You see this t in here? So as it turns out that this is a decay, an exponential decay with time. And this exponential decay with time, it depends on what, the speed at which it will decay depends on tau, and we call tau as the time constant. And it's very simple to compute this time constant depending on the circuit we have. And at this point, I'm only interested in calling it a time constant and explaining its effect. The other part in here, which I'll highlight in pink here, is what we call a steady state. This is basically these two parts that we highlighted in here, here, and here. So what I just showed you is we call it first order circuit, okay, because we can describe it with a first order differential equation. And the solution for this first order differential equation has two parts, a steady state part and a transient part. And it's transient because it actually decays with time and it disappears after a while. If you think about it, if t actually goes to infinity, you'll see that the whole term in here goes to 0. Because the e to the power of negative t divided by some sort of a tau actually goes back to 0, and you'll end up with just a steady state solution here, which is c. In our case, it was Vs or the 0. All right, so let me just spend a few seconds on the effective tau. So tau is what we call a time constant, and we can compute it in RC and RL circuits just by taking a look at the value of C and R and value of L and R at that point if it's an RL circuit. Anyway, the way we compute it doesn't matter. What matters is it just controls the speed at which the transient solution actually just disappears or ends. Okay. I plotted, what I've done in here is basically I took this equation that I just plotted and I gave it some sort of a value for C1, some sort of a value for C2, and some sort of value for tau. And you'll see them at the very top of all these graphs. So let me just read them for you very quickly. So in this particular graph, what I did is I basically said, the steady state solution will become 0. Basically, this is when we went down to 0. Basically, I'm at the 0 state in here. And initially, it was at 1. And that's what you see in here. You see that it was initially at 1 volt and it went down all the way to 0. That's what you see. So the speed at which it went, it's actually tau. The time constant is 0.5. That's what we have, a 0.5, and you'll see it's an exponential decay. Now, what's interesting in here is I actually put the t in here in terms of taus instead of actual values, because what I wanted you to see is at some point, which is 5 times the time constant, which is 5 tau, basically we reach that final solution here, or the steady state 0. That's what you'll see. Not at 4. At 4, we still have some, but at 5, you'll see that it's almost, that's it. It's stable. Like after 5 t's, 5 taus, that's it. And if you actually compute the 5 tau, remember it's like tau is 0.5 and that's 5. So that's basically 2.5 seconds or so. All right, so let's take a look at this particular one in here. In here, what I did is I gave it the same exact final value and the same exact initial value. So we go from 1 to 0. And you might think that these two graphs are the same. They're actually not, because the tau is different in here. It's actually at 10. But so at 5 tau, it's actually just simply 50 in here. But what I want you to pay attention to is exactly at 5 times the tau, you'll see that we reach the final value in here. So when I say in the next videos that we wait for a long time, that means I'm actually telling you, let's wait for 5, the time constant, so 5 tau. And that's similar if the steady state is actually the opposite direction. When we're actually charging the capacitor or charging the inductor, is pretty much the same. So in here, what I've done is I gave the steady state that I look for is 4. This is basically when we went to charge the capacitor, and let's assume that we're charging it with 4. So this is basically when we go up. And I said, well, the initial value will be 4 minus 10, which is here, negative 6. And we'll see it's an exponential. Instead of a decay now, it's actually an exponential incline. And the reason why it's an exponential, it's incline because the final value is more than the initial value. And in this particular case, I said, well, tau is 0.7. And you can compute the tau, 0.7, I think will be 3.5 in here. Okay, but again, what I want you to see is the following. So if this is 3.5 seconds, I want you to see that at 5 tau in here, what we happen to have is basically the final value. Similarly in here, I just changed the values a little bit. So tau now it's 70 instead of 7.5. So this one here is, instead of 3.5, it's actually 35. You'll see again at 5 tau in here, basically reach the final value. So whenever you see it like, hey, you wait for a long time, that means it's 5 tau.